Lesson: Vector representations of textual data. Understanding vector representations of textual data is essential for professionals seeking to implement AI solutions effectively, particularly within the domain of natural language processing. Textual data, inherently unstructured, requires transformation into a structured format that computational models can process. Vector representations provide a numerical form of text, enabling machines to analyze and interpret human language meaningfully. This lesson delves into the core methods and tools for achieving such representations, emphasizing practical applications and real-world challenges. At the heart of vector representation in NLP is the concept of embedding, where words, phrases, or longer text segments are mapped to vectors in a continuous vector space. One of the foundational methods is the bag of words approach, which represents text by the frequency of words within a document. While intuitive and straightforward, BAW often results in high-dimensional and sparse vectors, lacking semantic information. To mitigate these limitations, term frequency inverse document frequency weighs terms based on their importance across a corpus, thereby enhancing the representation by reducing the influence of common but less informative words. However, BODO and TF-IDF fail to capture semantic relationships between words, such as synonyms. Word embeddings, such as word2vec, address this by training a neural network to predict context words surrounding a target word, thereby learning embeddings that capture word meanings. For instance, in word2vec's skipgram model, the task is to predict context words from a given target word. This approach results in dense, low-dimensional vectors, where semantically similar words are close in the vector space. Word2vec has been widely adopted due to its effectiveness and efficiency. In a practical setting, professionals can leverage pre-trained Word2vec models available through libraries like Gensim to incorporate semantic understanding into their applications without extensive training resources. Moreover, Word2vec's ability to capture linear relationships between words enables analogical reasoning, as demonstrated by the famous king man plus woman equals queen example, showcasing the power of vector arithmetic in capturing linguistic nuances. Despite its successes, Word2vec has limitations, particularly in handling out-of-vocabulary words and understanding polysemy, where a word has multiple meanings. Global Vectors for Word Representation, developed by Pennington et al., aims to improve upon this by using a matrix factorization approach that considers global corpus statistics. Glove constructs a co-occurrence matrix of words and reduces dimensionality through matrix factorization, yielding embeddings that balance global context with local, word-level context. Another significant advancement in vector representations is the introduction of contextual embeddings, exemplified by bidirectional encoder representations from transformers. Unlike Word2vec and Glove, which produce static embeddings, BERT generates dynamic embeddings that vary based on the surrounding words, capturing context-dependent meanings. BERT's architecture, based on transformers, allows it to consider both left and right contexts simultaneously, making it particularly adept at understanding nuances and complexities of language. For AI implementation professionals, BERT provides a robust framework for tasks such as sentiment analysis, named entity recognition, and machine translation, where understanding context is crucial. Implementing BERT involves leveraging pre-trained models from libraries such as Hugging Face's Transformers, which offers a comprehensive suite of tools for integrating state-of-the-art NLP models into applications. For instance, fine-tuning BERT on a specific task like sentiment classification can be achieved with minimal labeled data, making it accessible and efficient for professionals working with limited resources. A practical challenge in utilizing these vector representations is dealing with domain-specific language, where general models may lack accuracy. Training custom embeddings using domain-specific corpora becomes necessary. Tools like Fast Text, developed by Facebook's AI Research Lab, extend Word2vec by representing words as n-grams, capturing subword information that improves handling of rare and out-of-vocabulary words. Fast Text's ability to generate embeddings for unseen words by averaging the vectors of its n-grams makes it particularly useful for specialized vocabularies in fields like medicine or finance. In real-world applications, choosing the appropriate vector representation method depends on the specific requirements and constraints of the task. For instance, when processing large volumes of text data in real time, computational efficiency becomes paramount, guiding the choice towards methods like word-to-vec or fast text. Conversely, tasks requiring deep contextual understanding may benefit from more complex models like BERT, despite their higher computational demands. Case studies highlight the transformative impact of these vector representations. For example, in e-commerce, product recommendations have significantly improved by utilizing word embeddings to understand customer preferences and product descriptions better. Similarly, in customer service, chatbots equipped with BERT have enhanced user interactions by providing more accurate and contextually relevant responses, leading to increased customer satisfaction. Statistics underscore the effectiveness of these approaches. For instance, the use of BERT in the Stanford question answering dataset resulted in a substantial improvement in performance metrics, surpassing human baselines in certain tasks. Similarly, fast text's application in language identification tasks across social media platforms has demonstrated superior accuracy, highlighting its utility in handling noisy and informal text. In conclusion, vector representations of textual data form the backbone of modern NLP applications, enabling machines to interpret and generate human language with remarkable accuracy. By understanding and implementing these techniques, AI implementation professionals can unlock new possibilities in text analysis, sentiment detection, and beyond. The dynamic landscape of NLP continues to evolve, with ongoing research promising further advancements in capturing the richness and diversity of human language. As professionals navigate this domain, leveraging state-of-the-art tools and frameworks will be essential in addressing real-world challenges and achieving impactful AI solutions.